Okay, in this video, I'm going to talk about internal energy. We're going to bring back in Q, and we're going to finally get to enthalpy. Enthalpy. Okay, so delta U is equal to Q plus W. We know that Q minus P dV integral is actually what the work is representing. So we can say that this equals Q minus P external delta V, for P external equals a constant. And we can also say that delta U is equal to Q minus nRT log of V final over V initial for a reversible expansion compression. Okay? And isothermal. Isothermal. Okay? But in each case, we can also say that delta U is equal to just Q if the volume is constant, for constant volume. Because if it's constant volume, VF and VI are the same, which means this is the log of 1. Log of 1 is 0, or delta V, 0, for no change in volume. So this indicates constant volume. And so now we can explore how the internal energy changes when we don't have any work component. Okay, recall Q is equal to MC delta T. This was probably from 116 days. I think you do it in biochem as well. So this is mass times the heat capacity. Actually, it's a specific heat if you're multiplying it by the mass times your delta T. Well, let's think about unit analysis. Again, I said you can do all of PChem with just a unit analysis. We know that Q is going to be in energy joules. So we've got grams and we've got Kelvin. So then what has to be the units of the specific heat? Well, that has to be joules per gram Kelvin. Cancel, 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 cancel. That means that joules equals joules. So what does this specifically mean? Joules per gram Kelvin. Okay, what is the definition of specific heat? Since the energy, J, needed to raise a gram by a Kelvin. Okay, so this is the energy you need to put into the system in order to increase the temperature. I'm going to get rid of the grams. I don't like grams very much. We're going to make this moles. So you could say Q is equal to NC delta T, where this becomes now the molar heat capacity. Okay, so heat capacity. I'm going to erase this and put a definition. Okay, so the heat capacity is the energy required to raise the temperature of a substance by 1 Kelvin. And so its units are joules per mole Kelvin, because we're going to be in moles for everything. Being grams is dumb. You should always be in moles. That's not fair. Theoretically, when you're doing like more theoretical based stuff, it's good to be in some unit that works for all substances. Grams is specific to that one particular substance, and so moles is a much better normalized value. Okay, let's turn this into a picture that we can then relate back to the understanding of delta U. So here's my box, gas molecules. Okay, if heat goes in, Q in, that would then represent, and the change, so here's my candle. Ooh. Okay, so heat's going in, and there is a delta T. So the amount of heat that's going in is causing that change in Kelvin. That's related to the heat capacity. Now remember, Q is not a state function. And because of that, you have to quantify the path that it takes, which makes it very challenging to do. This is why it's important to relate Q to U, and we do that through the heat capacity. Okay, so under constant volume conditions, because remember, delta U equals QV plus 0, so work is 0 for constant volume processes. That means that any heat that goes in is going into the internal energy, all right? So if we have Q going in, that means it goes into some place, and it's going to go into the molecules themselves. There it goes, going into the molecules, because the volume is not changing. The dashed lines show that this is a steel box or an iron box or some box that's not going to change its volume. So that means the only place that the energy can go is going to go into or internal to the molecules. Okay, so if that's the case, CV, and this is designating constant volume. Okay, anytime you see a little subscript letter, that represents that that parameter is constant, is equal to QV divided by your change in temperature. And again, I'm just taking the units here. So this is change in heat divided by the change in temperature. And because the change in heat is a path-dependent function, we just represent it as Q. Okay, so that means under this condition, this is just delta U. Well, actually, I should say it's du divided by dt. Cool? And this is the limit as delta t goes to 0. Oh, sorry. Yeah, okay, so I'm doing this backwards. I'm reading my notes backwards, is not the easiest. So this heat capacity is the Q divided by my delta T, and in the limit as delta T goes to 0, it then becomes dt. There we go, that feels better. Okay, and as we have constant volume, this becomes du divided by dt. Glorious. Okay, so if this is the case, this means that CV is equal to du dt, which means I can then say, and this is where the mathematicians get really mad at me, but that's okay, because we love each other in the end. So CV times dt equals du. That's awesome, because we're going to use this a whole bunch of times. Another thing that's really cool about this is contained within this relationship is the definition itself of the heat capacity. All right, you ready to see it? Okay, I'm going to move up here because I've run out of space. So going from this and recognizing that this volume is constant, I can say that CV is equal to the partial derivative of U with respect to T at V held constant. Cool. So U is actually a function of V and T. And because I've got volume constant, now I can just take the derivative with respect to temperature. That partial derivative of U with respect to temperature is my heat capacity. That's a number. You know, you've learned what this function is. You take the derivative of it with respect to temperature, you plug in the numbers for all the parameters, you get your value here. So cool. You want to see something else is really cool? I'm going to pause and erase. Okay, back again. Delta U for a monatomic ideal gas is 3/2 RT. For a linear gas is 5/2 RT, and then for nonlinear gas or nonlinear molecules in gaseous phase is RT, assuming equal partition. I'm wondering if you're seeing what's about to happen. So for monatomic ideal gas, CV equals partial U partial T under constant volume. So that means that CV is equal to what's the partial derivative of this with respect to T? The heat capacity of an ideal gas, monatomic ideal gas, is 3/2 R. And you don't need to memorize that because you know that if you take the partial derivative of whatever U is with respect to T and you have what U is, you can just determine what it is. CV for a linear molecule, 5/2 R, and CV for a nonlinear molecule in gaseous phase, 3R. Cool. Okay, now I'm going to relate this to the enthalpy using the heat capacity as an example. Okay, so for my heat capacity of an ideal gas, here's my little candle. Okay, so heat goes in for constant volume. This is constant volume. The heat that goes in goes internal to the molecules, okay? So CV is equal to du dt constant volume. What happens if I have constant pressure. Ooh, I'll make this easier. Constant P. So if pressure is constant and I'm putting heat in, the pressure is constant. That means that as the molecules bounce off the walls, their force per unit area has to stay the same. And if their force per unit area stays the same, as you put more heat in, what's going to happen to the box? Go team, it's going to expand, or well, it's going to expand most likely. And so, which makes sense because of Charles' law, as the temperature increases, the volume is going to increase. So at constant P, the heat capacity is going to be equal to the change in Q at constant pressure per T at constant pressure. So that heat energy not only goes into the molecules, it also goes into the expansion of the box under constant pressure because the pressure has to be maintained, which means the volume has to expand. So we've got heat Q going into the molecules and, actually I'm going to write it down here, plus into expanding the box. Okay, two different types of heat. One goes into the molecules, which is really just this one. The other one goes into expanding the box, which is this additional bit under constant pressure conditions. It's enthalpy. Okay, so let's derive this using the alternative method, or the actual method, which is relating it from the first law. Okay, so du is equal to dq at constant pressure minus p dv. Okay, so there's my q and there's my work. And again, under constant pressure conditions, I've pulled this p out. And so now it's no longer, it's going to be not a reversible process. This is against a constant p external. Okay. So this means that if I solve for this, this gives me dq pressure is equal to du plus p dv. Okay, so now what I'm going to do is I'm going to show that this is going to change from one state to state 1 to state 2. And so this says qp is equal to the integral of du from initial to final plus p dv initial to final. Okay, so this equals u final minus u initial plus p v final minus p v initial. Cool. So now I'm going to put my initials together and put my finals together. U final plus PV final minus U initial plus PV initial. Everyone happy with that? Here's my state 2. Here is my state 1. And I've got Q at constant pressure. Awesome thing about this, the reason that we use the first law the way that we do is because this is a state function. This is not. We were able to change this into a state function to relate it to dV, but we do have pressure changing along an isotherm that we know if we use the ideal gas model. See how it gets complicated? So we need a new state function, and we got one hidden here. Final minus initial. That is a state function equal to a non-state function. First law. So this means that we need to name this something. Let's call it H, because why the hell not? So this is H2 minus H1. So that means QP, oops. So if H is equal to U plus PV, when we call this enthalpy, then that means Q at constant pressure is equal to H. Or actually, sorry, delta H. That looked weird. Delta H! May I introduce the enthalpy? Enthalpy then is equal to the internal energy plus the change in PV. Remember what PV is? That's expansion work. Cool. So that means if you think about this picture of the heat capacity at constant pressure, heat's going into the molecules, delta U, and it's going into expanding the box such that the pressure remains constant in here. Expanding the box is pressure volume expansion work, delta PV. Go team. So now we have two state functions, one representing energy going internal to the molecules and the other one representing the combination of the internal to the molecules and the additional expansion to maintain constant pressure. Fun? So what we can do then is we can say that the heat capacity CV is equal to du dt at constant V, and Cp is equal to dH dt at constant P. Within the definitions of the heat capacity are contained almost everything you need to know or should know about the first law of thermodynamics in terms of the differences between the internal energy and the enthalpy. Go team. Okay, that's a lot. Ask questions when you have them. Yay!